approximation, transition to multivariable functions. Okay, so let's take a look back in Math 153. That's Calculus 3 for some of you. Looking at Taylor series. And for a reference here, you can check out Paul's online notes. I got a little link there at the bottom there. So if you're looking back and go like, hey, who's this Taylor dude? You can check that out. All right, so now what we're looking at here is this is a way to approximate functions or to actually represent functions based upon the derivatives. So you got to have the derivative values there. That's why the A is there, because we're actually going to get numbers there. We're going to do the derivatives, plug in numbers, and then get the results, and then we'll use that for this series expansion of a function. Now, how we can use this is that here's a shortened version of it, just the first three terms of this Taylor series, just expanding it for the first three terms. And I just kind of want to bring your attention to that. If you just use the first two terms here in this Taylor series, you get a linear approximation. Okay, so you're using the first derivative there. So just notice you're using the first derivative there, and that gives you your slope. It's an estimate of the slope of the line in that neighborhood of the graph. And so that's kind of the first two terms, linear approximation. But then, hey, notice there's a power 2 right here. So if you throw on that third term with it, you got the quadratic approximation. So looking back at Taylor series for one variable, we can actually come up with a quadratic approximation for it using the first three terms of the Taylor series. Okay, so now what we want to do is extend this idea to multivariables. Okay, so that's what we're going to be doing here. So we're going to extend it. So we're going to take this this Taylor series here. We're going to extend it. We're going to come up with a linear approximation and a quadratic approximation. Okay, so one of the first transitions that we have here is we're going multivariable. So we've got an x and y. And then so for that first term there, that's the value, that's the point on the graph for a single variable. So we want the same thing in multivariable. We want that point as well. So we'll be using that. So now to get to the next term here, just recall that in multivariable, we've got two partials. We got a partial with respect to x, giving us a slope in the x direction, and we got a partial with respect to y, giving us that slope in the y direction, following those trace lines. Okay, so that's our extension from the single variable to our multivariable for the linear approximation. So we're using that initial value plus the partial derivatives there. That's given us the slopes. And again, we're plugging in AB into each of those partials to get a numerical value so that we have kind of like slope in those directions. So now we want to extend it and we want to work on it and get that the quadratic term involved, that power 2 there, using the second derivative. But wait a minute, when we're talking about second derivatives, we're talking about that partial. So we're going to have the second derivative there with an xx there. So that's the, doing the partial derivative with respect to x and then doing it again with respect to x. And then, of course, we've got the other version. We've got the partials with respect to y. And of course, when we do the partial with the x's, we're using x minus a here to the quantity squared. And then when we're using the y direction, we're using y minus b. You might be wondering like, dude, why don't we use x minus b over here as well? Because here's why. If you're going within the y direction, okay, so you're doing the partial with respect to y, you're kind of holding the x constant. So that x minus b is not, or x minus a is not changing. And so you're still on the a line there. And so that's going to be 0. So that's why you don't include it. Okay, so we're just talking about the change in that y direction. And so we've got changes for y, not for the x. Okay, so that's what we got. But just a little note here, don't forget about those mixed partials. So we've got two more terms when we're talking about quadratic approximation with respect to multivariables. And so we're going to be doing the mixed derivatives here. So I've got the partial with xy, and then I've got the partial yx, and of course you get the 1/2. That's from the Taylor series expansion. And so when we're doing the mixed partials, we're going to have a combo of x minus a and y minus b, and then vice versa, the y minus b or x minus a. Of course, these could be switched around. They're only multiplication. And so that is our extension to the quadratic approximation of a function. And we're using all these pieces here. Oh my gosh, there's one term, 2, 3, 4, 5, 6, 7 terms here that you got to keep track of. But now, if we have a continuous situation, excuse me, we got a continuous situation here, just remember Claro's theorem that basically says if we're talking continuous, if our partials are continuous, our mixed partials are continuous, then we've got the two partials are actually equal to each other. So then we can combine those two terms from the previous slide. So those bottom two terms, these two terms can combine because basically these are equal to each other. And so those halves combine together to make a whole. And so we just have this one term here. So we can at least reduce it by one term. Okay, so here is your formula for doing a quadratic approximation in multivariables. All you need to do then is whatever function you're playing with, you get its value, you get its derivative, plug in your a and b for both the x and the y's. Then you do your second derivatives, higher order derivatives there, even your mixed one right there. And then just basically plug in your values, plug in your a, b's all the way across, and then expand it all out if you want to, combine like terms, and then you have your quadratic approximation. Thanks. Hope you enjoyed this show. Have a good day. Bye-bye.